So this is the 11th session on signals and systems, and we continue our study of operation on signals. And in this session, we are going to study an operation called as a time shift operation. All right, so let us start. So time shift. Now suppose you have a system which is providing a time shift. And let us say that the input to this system is some signal which we call as xt. Now this time shift can be a delay or advance. Let us first assume that the system is providing a delay. In that case, the output is designated by the symbol xt minus d, where d is the delay. So if xt is any signal, xt minus d is essentially xt itself but shifted by d seconds, shifted to the right by d seconds, delayed. How to show this? So let us first assume some instant of time, let's say t equal to t1. So xt has some value at t equal to t1. Now xt minus d will also have the same value when t minus d itself is t1. That means the time at which the delayed signal has the same value is going to be different. So what will it be? Let us see. So t equal to t1. At this we evaluate xt, and we want t minus d also to be t1 at this point. So t minus d is equal to t1. In other words, t is equal to t1 plus d, which means at whatever instant the value of xt is known, the same value is attained by xt minus d seconds later. Doesn't matter which time you are considering or which value you are considering, it's always delayed by d seconds. So as we said, signal is delayed by d seconds, it shifts to the right. So let's see an example of this. In this case, our signal is a triangular pulse. So it starts from t equal to minus 3, increases linearly, reaches the value of 3 at t equal to 0, then decreases linearly and becomes 0 at t equal to 3. These are our pulse. Now in order to provide facility for sliding to the right or sliding to the left, which we shall see in the next slide, we require a better time slice here. So although the signal itself is existing from minus 3 to plus 3, what we are doing is we are using the complete time period of minus 10 to plus 10 seconds. Okay. Now in this case, if we assume that delay is 3 seconds, then this entire waveform will shift to the right by 3 seconds. So you can see that here the waveform had a maximum value at t equal to 0. In xt minus 3, it has a maximum value of, note this, 0 to 4. So this is 3 and it has a maximum value. In fact, all the corresponding points, every point on this waveform in fact is shifted to the right by d seconds or 3 seconds in this case. For example, this was minus 3, so that is shifted to 0. And this was 3, so that is shifted to 6. So this is an example of how the waveform will look like when it is shifted by certain amount of time. Alright. Now in this case, we have considered delay. Now let us look at time advance. So if xt is my input, output will be written as xt plus d. And again, we consider any instant of time t1, then these two will be same at different times. And how do we calculate that? So if you consider an instant t equal to t1, then for this waveform to have the same value, the term within the bracket must be equal to t1. So t plus d is equal to t1, or in other words, t is t1 minus d. So it occurs at a time which is earlier than this. So it is advanced. In other words, the waveform shifts to the left. Okay. So signal is advanced by d seconds. Now it's important to note that this operation is not possible in real time. See, delay is possible in real time. Suppose you read some sample. You can always wait for a certain amount of time. You can store that sample value and then wait for a certain amount of time before you throw it to the output. So you get a delay. But at any point of time you read the sample value, there is no way to go back in time. So time advance can never occur in real time. However, when we talk of time advance of signals, we often mean that all the sample values have been already obtained and they have been stored over a certain time slice. And then by considering a particular origin, with respect to that origin, we can talk of time advance of the signal. So understand that this is possible only for a stored signal. Time advance is obviously not possible for a real-time signal. All right. So this is an example. Again, we are considering the same triangular pulse in this case, which is existing from -3 to +3, and it is advanced by 4 seconds. So this 0 where you get the peak in the advanced signal at t equal to -4. You can see the entire waveform is shifted to the left. Okay. Now, before trying to understand how to delay or advance any given signal, what we are going to do is to first look at the functions which will allow us to generate a delayed ramp and also allow us to generate delayed unit step signals. The reason for this is that once you have these programs, it will be possible for you to use these programs repeatedly in order to generate any piecewise linear signal that you want. And then we will study the shift operation. All right. So as I have already said, these are useful signals, as many piecewise linear signals can be obtained by judicious application of delayed ramp and delayed unit step. So let us try to see the function for generating a delayed ramp. So if you use this function, you call this function, this is the input and this is the output. So this is your unit ramp. So for negative values of time, it is 0. For positive values of time, it increases with unit slope. You can see the base here is 6 units and the height is also 6 units. So the slope of this is unity. And then when you run the function for delayed ramp, you get RT minus 2. So the whole thing is delayed by 2 seconds without affecting the slope. So this 0 going positive becomes 0 going positive at t equal to 2 seconds rather than at 0. So delayed by 2. Slope remains same, although it may look higher, but scale is different. You can see here the highest point here is 4, and as you go from 2 to 6, the base units are also 4, the height is also 4, so the slope has not changed. Okay. So how do you write the function to generate the delayed ramp? So what you can do is initially you can put all the output values to 0 and then locate where is your D, whether it is a delay or advance, and once that D is located, then you write the equation for the straight line. Okay, so it could be advance or it could be delay. Alright, so let's see the function for generating ramp with delay or advance. So function R is equal to ramp D. This is the name of the function, and there are 3 parameters which are input to this function. T is our usual time array, M is the slope of the ramp generated that we want, and D is either the advance or the delay depending on the sign for this D. As we shall see, if D is equal to negative with some quantity, for example it's -2, then it will be delay, but if it is +2, it will be an advance. Alright, so these 3 are the input parameters for this ramp D function, and the output parameter is of course the ramp itself, that is this R. This is an array. So what is the first thing you do? N equal to length of T, so that first you can generate the entire signal over all time having 0 values, and then you can modify that. So what you do, first make R equal to zeros 1, n, and then you get into the loop to find out where the D lies, whether it is advance or delay. So you get into the loop for I equal to 1 to n, and if Ti is greater than equal to -D. Now note here we have written -D. So if d itself is negative, for example, if d is minus 2, then this quantity will be plus 2. And we are saying if ti is greater than plus 2, then you generate your straight line, which means it's a delay. So instead of starting from 0, it will start from 2 seconds. So if d has a negative value, it means delay. If it has a positive value, then it means it's an advance. Then use your straight line equation, m into ti plus d. That is your straight line equation. Okay. And then of course this is the end for if, and for this is the end, and then you require an end for the function itself. All right. So now let's see how to use this function, the calling program. So first you define your time vector, let's say from -6 to +6 with a time slice, with a sampling time period of 0.01. This could be lesser than this. For example, for better results, you can use 0.001, 0.0001 and so on. But 0.01 gives reasonably good results, so we can check for that. M equal to 1, so we are going to use unit slope itself. And now, so t is there, m is there. So what we do, first we generate our ramp, which is the normal ramp starting at the origin itself. That is why we have this last digit that we have provided is a 0. There is neither a delay nor there is advance. So that is your R. And then R1 is ramp D, T, M, and then -2. So we are going to delay with the delay R by 2 seconds and then plot both the waveforms in order to see how the function works. So that is standard. Now 2 plots, so subplot 2, 1, 1, plot TR first, line width, etc. And then you plot TR1. So when you do this, this is what you get, this is what you expect. So this is my input to the function and this is the output. Of course, input is in terms of T, M and the delay. This is assumed. That is a part of the program itself. So this is your RT and this is RT minus 2. So we have seen how to write the function and how to use the function for providing a delay for the unit ramp. Something similar you can do for unit step also. So let's first look at the function for the unit step. Now in this case, note that for unit step, you don't need the third parameter as the input because there is no such thing as a slope here. For ramp, we had a unit slope or whatever slope we wanted. But for unit step, we starts at 0. It is constant at 1 for all the other values. So you don't need that parameter at all. So input parameters are T and D. And again, if T is negative, it's a delay. If T is positive, it's an advance. And use the output. So as usual, again, n equal to length of T. First generate all zeros. Then locate D. So if Ti is greater than minus D, now you don't need you don't need the equation for a straight line. You can just write ui equal to 1. And then as usual, end for if, this end for loop, and this end for the function. Okay. So if you call this function again, -6 to +6 with a sampling time period of 0.01, then you call the uStep function, but T0 first, normal unit step, and then generate U1 with an advance of 2 seconds. Note we have written +2 here, there is no minus sign, so this is going to be an advance. And then of course, as usual, you plot the normal unit step function and you also plot the, so you can see this is your normal unit step function plotted over -6 to +6, and this is now advanced by 2. You can see that here it was starting from 0 and here it is starting from -2 seconds. So the whole waveform is shifted to the left, so it's an advance. All right. Now the reason for studying these functions was that you can generate any piecewise linear function by using repeatedly the ramp function and the unit step depending on the waveform. So I'll illustrate it with one example. You can try other examples yourselves. So using ramp and step functions. So suppose we want to generate this signal. Look at this one. So here the time window is from -4 to +4, and this is a triangular signal which is starting from -3. At 0 it reaches a value of 3. That means your slope is unity in this case. As you can see, base is 3 units, height is also 3 units, so the slope is 1. And from 0 to 3 now you have a negative slope. Now we want to generate this by the repeated use of ramp functions. In this particular case, it so happens you don't need the unit step, but you use only repeated ramp functions. So what are these functions? So let us see. First of all, you want to generate this part. Okay, so what you do, you write R1 equal to ramp D T13. What does it mean? T is the time array, 1 is the slope. We have seen this is a unit slope. Okay, and 3 is the advance. So because it starts from -3, therefore when you execute this, you get this part. However, we can't use only this part, because once you reach t equal to 0, you want to reduce this. Incidentally, note, this is written in two ways. This is the way it is normally used, written in textbooks, and this I have used, this particular equation I have used in order to denote the use of the ramp D function, and this is how it is normally written in your textbooks, theoretical formula. So RT is a unit ramp, and t plus 3 means it's advanced by 3 seconds. Okay, but here we actually write the function itself. Okay, so this is it. Now what we want, from beyond t equal to 0, we want to cancel the effect of this part, because now we want to reduce this, we want a negative slope. So if you generate a ramp with a negative slope, the question is what should be the slope? And the answer to that is, if you use this slope which is negative of this value itself, then you will get a constant. So you will require double the slope. So what you do now, you provide R2 equal to ramp D, T is our time array, -2. So slope is now negative, and it's double the slope of R1. This is what we wanted. And delay is 0, because at this point we want this to be introduced. So you can see this is 0, and this is now this one. So that is your R2. Finally at 3, see, if this was not cancelled, it will continue like this, but we want to bring this to 0 at t equal to 3 seconds. So from t equal to 3 seconds, you now require a straight line which is opposite to that. So you require a positive slope and equal slope, so that the two cancel out and you get a 0. So note that here you had -2 slope, but resulting slope was only unity. Okay, so as you can see from here, this 0, 1, 2, 3. Okay, and this reaches this -5, 4, -3 it reaches. So it has a unit slope from here to here. It has a unit slope in fact, but negative. So we provide a unit slope which is in the positive direction, so that will cancel this part. So it is starting at 3, so delay of 3 seconds. So that starts from here, unit slope, and that cancels. So that is how you generate. So now you sum up all these. So R1 plus R2 plus R3, this is what you get. So this explains to you the technique of generating a piecewise linear function with a specific example. So you can imagine some different piecewise linear segment function and try to see how you will use ramp repeatedly or unit step as required. So those exercises you can do yourself. But I hope this illustrates to you the technique of doing it. Alright, let's now look at the program. So that is straightforward now. This is your time slice. You generate R1, you generate R2, you generate R3, add all of them and then plot. So these are the usual statements which are required for plotting. So I'm not spending too much time on this. If you need, you can pause the video at this time and go through this, but it will simply plot the output like this. So it plots R1, it plots R2, it plots R3, and finally it plots the sum which we have already seen. All right. So what we have studied so far is how to generate a delayed or advanced ramp, how to generate a delay or advanced unit step function, and how to use these function in order to generate any piecewise linear function that you may be interested in. So you'll get some xt by using this. And we would now like to study the shift function. So what is the shift function? Y equal to shift txd. So t is the array, x is the input. So from where this x comes, as I told you, is basically a piecewise linear function which you can generate by repeatedly using unit ramp and unit step. And then this is the d, that is the delay or the advance. Now y equal to interpolate 1. So there is a direct function available in the MATLAB which will enable you to generate shift without having to code yourself. So what are the parameters you pass? You pass t, you pass x, that is the input signal, and then you pass t minus d. Okay. So once these parameters are passed, this will actually generate a shifted signal. But one important thing to note is that when we are calculating this t equal to t1 plus d and calculating the function value, note that our sampling time interval ts may not have one-to-one relationship with d. But what I mean is its relationship may be such that the time that you get, at that time you do not have the value of the original signal. That is possible. That is why it does the interpolation, and it does linear interpolation. And for any times which are outside this time range that you are providing by this t array, it will simply append 0. So we are not going too much into the details of how this particular function works, but the point is you provide t as input, x as input, t minus d as input, write linear, write 0. These are all inputs, and this is your output. So that's all you need. Now, using the shift function. Okay. So what we are doing, t equal to minus 10 to plus 10, then R1, R2, R3, x we generate. Okay. Once we have generated x, now we want to use the shift function to shift x and then plot them. So subplot 2, 1, 1, etc. and you can plot it. So this is my xt, because remember all these functions are such that it is actually generating a triangular pulse that we studied earlier, and the shift function will shift it to the right by 2 seconds. So in this particular case, we have specifically studied how to do programming for providing delay or advance to the continuous time function. And that's all in this session.